In this video, we are going to do several exercises designed to determine configuration of molecules with single center of chirality. First, let's briefly review allowed transformations of Fisher projections and perspective formulas, as we will need them when determining RS configuration. Exchange of position of two substituents in pairs is allowed, so we can, in either Fisher projection, flip two substituents in pairs, or in perspective drawing. 180 degrees rotation is also allowed, but that's usually of little use when determining configuration. The other transformation that is allowed is exchange of positions of three substituents, clockwise or counterclockwise, while keeping the fourth substituent in its original position. And here you have an example with Fisher projection formula and perspective drawing. So let's look at the first example. So what is the configuration of this compound? This is a hydroxy acid, actually lactic acid, trivial name. So first we redraw the molecule in such a way that we show all the bonds. And even though there is carbon-oxygen double bond here, actually we don't need to rely on virtual bonds and virtual atoms in this particular case. Usually we do, but in this particular case we do not. And you will see in a minute why. So chirality center is obvious at the intersection of the two lines or four bonds. Four substituents are oxygen, hydrogen, and two carbon atoms. Obviously, oxygen with atomic number of 8 has highest priority, so it's priority 1, and hydrogen lowest priority, priority 4. Now, two carbon atoms have the same priorities, so we would say that's a tie. But then when we look at the next atom, one carbon is methyl group, CH3, so all three substituents are hydrogens. The other carbon has two oxygens bonded to it. So even without converting double bonds into equivalent number of single bonds and dealing with virtual atoms, we know that top carbon is going to have higher priority, simply because it has oxygens attached to it, while the other carbon has only hydrogens, lowest priority substituents. So we can confidently assign top carbon priority 2 and bottom priority 3. And now we are done with assignments. Now at this point it's a very good idea to remove substituents, to redraw the molecule and only include numbers that represent a priority order. That way you won't be confused with substituents, and also if you are redrawing and manipulating formulas, you won't be wasting time drawing large substituents. And so just make sure that you indicate the order of priorities correctly. So this is the order of priorities, and we can see that substituent with priority 4 is on horizontal bond. That means it's projecting towards us. It has to be on vertical bond in Fisher projection, so that it projects away from us, away from the viewer, so that we can ignore it. So we should, for example, move it down to position where substituent 3 is. That means, of course, that we need to do one of the allowed transformations. For example, rotation of 3 substituents. In this case, that would be counterclockwise, while keeping 4th in place. So we can exchange positions of substituents 4, 3, and 1 counterclockwise, while we keep substituent 2 in place. And this is the new arrangement. So you can see that substituent 4 is now on a vertical bond, and that means we can now ignore it. So substituents 1, 2, 3 make clockwise array, and that means that this is R enantiomer. And I already mentioned, trivial name is lactic acid, so this is R lactic acid. Next example is 2-butanol, and it's perspective drawing. So now we have an example with perspective drawing. We should redraw this drawing to show all the bonds, so complete structural formula. And now we can assign priority 1 to oxygen, obviously higher than hydrogen or 2 carbons attached to chirality center. And we can assign priority 4 to hydrogen. That's obvious that it's the lowest priority substituent. Next, we have 2 carbons attached to chirality center, so that's a tie. They have same priority. Now when we look in each substituent next atom of highest priority, we can see substituent on the left has carbon, on the right hydrogen, so carbon has higher priority, So that entire substituent has higher priority, that's priority 2, and remaining substituent priority 3. Again, we redraw this formula in such a way to show only chirality center and indicate order of priority of substituents. And again, we can see that substituent priority 4 is projecting towards us. So we need to move it into position away from us, where substituent 1 is. So to do that, we'll move substituent 4 to the back, and we can exchange those two substituents in pairs. So flip positions of substituents 4 and 1, that will place substituent 4 in the correct position in a bond that projects away from us. But to keep this the same enantiomer, we also have to flip positions of substituents 2 and 3 simultaneously with flipping 4 and 1. And we end up with this arrangement. Now that substituent 4 is projecting away from us, we can ignore it, and we can see that substituents 1, 2, and 3 make clockwise array, so this is R2-butanol. Now we have a little bit more complex example. Of course, first step is to redraw the molecule in such a way to show all the bonds. And from this drawing you can see that this is not simple. You cannot quickly determine the order of priorities. Now we have to use virtual atoms and virtual bonds. So we redraw this molecule in such a way that each double bond is converted to equivalent number of single bonds. So each double bond is the same. It's carbon-oxygen single bond. So double bond. So we redraw it as carbon-oxygen single bond. On each carbon, we add additional bond shown in blue, and on each oxygen additional bond. So for each atom, double bond has been converted to 2 single bonds. And for each atom, at the end of the bond, there will be atom that is at the other end of that double bond. So for carbon, at the other end, there is oxygen. So at the end of virtual bond, there will be also oxygen. For oxygen, at the other end of double bond was carbon. So at the end of virtual bond is carbon atom. We do it for all 3 double bonds. And now let's look at order of priorities. When we look at all 4 substituents, all 4 atoms directly bonded to chiral carbon are carbon atoms. Therefore, it's a tie. They have same priority. Now, in each chain, we should determine which atom has highest priority and indicate that atom and follow that up. So let's start with top substituent. So we have 2 oxygens and hydrogen. Obviously, oxygens have higher priority, but oxygen that has substituent has higher priority than virtual oxygen that has no substituents. So that's the atom that we are now considering. And for same reason, this is the oxygen that is highest priority substituent in this substituent that points to the left. There are 2 oxygens that have substituents, but one has carbon, the other one has hydrogen. Even though carbon is virtual carbon, it still counts as a carbon, no difference compared to any other carbon. So that's higher priority paths. Next, again, this substituent is very similar to the top one. Again, oxygen attached to carbon, highest priority. We have oxygen, oxygen, carbon, so this oxygen highest priority. And finally, here we have hydrogen. So now when we look at second atom in each chain, we have 3 oxygen and 1 hydrogen. So we can assign priority 4 to this substituent, because that's obviously the lowest priority substituent. Now, with remaining 3 substituents, we have to keep going following this chain of highest priority, and we end up with 3 carbon atoms. That's a tie. So highest priority path in these 3 chains is the same. In all 3 chains is the same. Now we have to follow the second highest priority path. And so second highest priority path, shown in light blue, is now second highest priority atom on these carbons directly attached to chirality center. So that's oxygen. Here it is, we have 2 oxygens. Of course, in the first case, it was oxygen versus hydrogen. So it's easy, it's oxygen. Now we have 2 oxygens, but one has hydrogen as a substituent, so that's higher priority path. And it's also oxygen. So now we have 3 identical substituents, again a tie. So we look, following that second highest priority path, we look at next substituent. And actually we have only one substituent. We have hydrogen. On the other 2 oxygens, because they are virtual atoms, we have no substituents. So substituent attached to those oxygens, if there are no substituents, they have priority 0, or atomic number of 0, while hydrogen has atomic number of 1. That's the only time when hydrogen has higher priority, when it's hydrogen versus nothing. And so this substituent has priority 1, because it has higher priority compared to other two substituents. And finally, for remaining two substituents to make a difference, we have to look at third highest priority pathway. That's actually a least priority pathway of least priority. And we have hydrogen versus carbon. Carbon has higher priority, so it's priority 2 and priority 3. Now, as usual, we redraw that to simplify, and to avoid any confusion, we only redraw Fisher projection showing priorities instead of atoms. And again, you can see priority 4 substituent is on horizontal bond, projecting towards us. It has to be on vertical bond. So we can move it, let's say, down to where substituent 2 is, and we can move substituent 2 to position 4. So we can flip 4 and 2 in pairs, and of course, to maintain same enantiomer, we have at the same time to flip positions 1 and 3, flip substituents 1 and 3. And we end up with this new formula, where substituent 4 is on a vertical bond, as it should be, and now since it's projecting away from us, we can ignore it. Now, substituents 1, 2, 3 make counterclockwise array, and this is S enantiomer. Now, we have another example, slightly more complex than the previous one. Again, a lot of multiple, or actually one multiple bond, but it's going to make things rather complex. So we redraw the molecule in such a way that all the bonds are shown as simple. We have carbon-nitrogen triple bond. So we have to convert that to equivalent number of single bonds. So we redraw that as carbon-nitrogen single bond, and on each carbon and nitrogen we add 2 more single bonds shown in blue, so those are virtual bonds. For carbon, at the other end of triple bond there was nitrogen atom. So for those virtual bonds, at the other end we'll place nitrogens. For nitrogen, at the other end of triple bond was carbon atom. So for nitrogen, at the other end of each virtual single bond we place carbon atoms. So now we have appropriate complete formula where we can determine order of priorities. So first we look at atoms directly bonded to chirality center, and we find that there are 3 carbons and 1 hydrogen. Hydrogen has clearly lower priority compared to 3 carbons, so that's priority 4. Next, we look at atom of the second highest priority in the remaining 3 substituents, and that's nitrogen. Let's look at top substituent. We have 3 nitrogens attached to carbon, but one of the 3 nitrogens is attached to 2 other virtual carbons, so that has higher priority compared to 2 nitrogens that have no substituents. In remaining 2 substituents, we have only nitrogen versus hydrogens, or actually left one is nitrogen versus 2 hydrogens, and bottom one nitrogen versus actually also 2 hydrogens, so it's the same thing here. So nitrogens are the highest priority atoms. So we have 3 nitrogens, so that's a tie. We go to third atom in each substituent, and so we have top one is carbon, one to the left is hydrogen, and bottom one is carbon. So we have 2 carbons and a hydrogen. So clearly hydrogen has lower priority than the other 2, so that's priority 3. And for the remaining 2 substituents, we have to go one step further. So it's hydrogen versus no substituent. So hydrogen, atomic number of 1 versus no substituent, atomic number of 0, that's higher priority. So bottom substituent has higher priority, and that's priority 1, top substituent priority 2. Note, looking back, that triple bond has lower priority than bottom substituent that has only single bonds. I intentionally included this example because I have seen online exercises where there is an advice given to students that to avoid using virtual atoms and to speed things up, simply assume that multiple bond has always higher priority compared to single bond. And that way you can avoid all the hassle with virtual atoms, and things work much faster. That works only 60 or 70% of the time. And so those are not very good odds for the exam, so I can tell you, don't do that. I intentionally selected one example where that doesn't work. And so now, as usual, we redraw formula to show only order of priorities to avoid any confusion with large substituents. And substituent with priority 4 is on horizontal bond. It has to be on a vertical bond, so we should move it to the bottom where substituent 1 is, and we can shift position of 3 substituents clockwise while keeping substituent 2 in its position. So we end up with this arrangement. Now we can ignore substituent 4, it's on vertical bond pointing away from us, and substituents 1, 2, 3 make clockwise array, and this is R enantiomer. So this completes exercises, and now next we are going to look at molecules with multiple chirality centers.